We're going to look at Lab 6, Question 2a by hand. I'm probably going to there might be a number of videos to kind of address everything this evening and tomorrow. But one of the things is I can definitely say that you'll see you'll see in a later video where you went wrong. I won't go too long on it, but let's do it right now. So we have a differential equation. Have I got this pen working? No, I don't. Oh god, pause. Okay, we're back. So stuff that I'm fairly sure you did good was, so you had second derivative of bending moment with respect to distance is minus cos x squared minus 1. Now, one thing that has to be said here, if you ever have sine and cos or tan mixed in with derivatives, you have to be using radians. I don't know if that's something that made you go awry here. I'm actually not sure how you knew that you weren't getting question 2 right, because there's no answer there. Okay, so what you did, which was good, was you said essentially that v be the first derivative of bending moment, which is actually the shear force, and then therefore if I differentiate both sides here, so this is stuff that you've done well. If this, we'll be able to write the this boundary value problem, which just says that the bending moment at 0 is equal to the bending moment at 6, which is equal to 0, as two first order initial value problems. So we'll have one for m. So the derivative of m with respect to x is v, and the initial value of m is 0. And we have that the derivative of v with respect to x is the second derivative of m with respect to x, which is this minus cos x squared minus, excuse me, get the bracket right, minus 1, and the initial value of the shear force is unknown. So let's set us up with a table. Now I need to take two shots, so I'm going to have actually going to have a big enough table, because I think there's something that you're missing out. So you have x. Actually, yeah, the table, actually I won't write the full table. No, I won't. But let's do a little bit of the table. So we've got x, we've got m, and we've got v. Okay. We'll take our first shot here, something like this. The x goes from 0 to 6 in steps of size 2. So it's 0, 2, 4, 6. And I think this is where one of the problems you had, you weren't using the previous x. The starting value of m is 0, and the starting value of v essentially we make up. So we're going to take a guess. Let's shoot straight at it. Let's take v of 0 equal to 0. So we're going to go with this. Now what we're trying to get here is a 0. Okay. Now I actually don't have a calculator. So for full disclosure, I have I've done this in Excel in front of me. So that's where the numbers are coming from. Okay, so we'll do it in this order. We'll do next m and then next v. So I think you were using kind of this m2 notation. Now that wouldn't be ideal. So in terms of notation, this is called m1, this is called m2, and this is called m3. And these are approximations of, say for example, m1 is approximating the bending moment at x equal to 2. That's kind of the notation. So those subscripts just mean, first the numbers that you're basically generating. So it means that the first, say, grid point, I don't know what the technical name for this 0, 2, 4, 6, I'll call it grid point. So along the beam here, 0, 2, 4, 6. So the subscripts 0, 1, 2, 3. So it just means that the 0th point, the first point, the second point, the third point. Okay. So we're going to calculate m and m1 here. So m1 is equal to the previous m value. So we're at now I'm going to be rubbing this out, so it'll be kind of almost an animation. So m1 is the previous m value, which is above it, which is 0, plus the step size, which in this case is 2, times the derivative at the previous point. The derivative of m is v, and the value of v at the previous point is 0. So we get 0 here. So I'm going to rub this out. So we get a 0 here. And now we must calculate the next v. So the next v value is equal to the previous v value, which is 0, plus the step size, which is 2, times the derivative evaluated at the previous point. Now this is the bit that you missed. The previous x value for the first one is 0. I think you might have been using 2 or something like that. So we're going to have minus cos the previous x, so previous to here, is 0. So this will be cos 0 squared minus 1. And I'm just looking at the Excel there, it gives me a minus 4. Okay, and we'll go again. So m2 is equal to the previous m value, which is still 0, plus 2 times the previous slope, and the derivative slash slope of m is v, and the previous v is minus 4. So we get minus 8 here. And then v2, so it'll be the previous v, which the previous v to here is minus 4, plus the step size, which is 2, and then the derivative of v is minus cos x squared minus 1, but what's the previous x to here is 2. So this will be 2, and my Excel tells me this is approximately, now you should probably use five significant figures. Just looking on the point there, it's lovely. Not the problem at all. Okay, and now I need to get my M3 as such. To get this thing. So I'll probably rip too much off there. Okay, so M3. Now M3 is at the third point. Well, the 0th point is the initial, and then the first point, second point, third point is the previous m value, which is minus 8, plus step size 2 times previous v value, which is minus 4.69271. And 5 significant figures, I'm getting minus 17.385. Minus 17.385. Now I store this, keep this value. Now in terms of the formula, this is going to be my YA, my first shot. Now, of course, I'm actually trying to hit 0 because the bending moment at the other end of the beam at x equals 6 is 0. So we go again. So that was kind of an undershot. So we'll pick a bigger value now. So V0 we're going to try is 10. And actually I should go back. This is like my VA. Okay. So I'm not going to go through the same thing again, but what's important to look out for is that you're using the slope at the previous point, and you're using the previous x value. And if we carry this through, M3, which remember is an approximation to M6 with this guess that the initial slope is 10. And okay, so this is kind of where M3 is approximately that. M3, now all I'm going to do here, I'm just going to change the V on the Excel. The other thing, yeah, okay. So that's 42.615. And that plays the role of my YB. Now I think the other thing you didn't do in your answer correctly was actually finish off the question, because the question is actually looking for these two values. If you look at the, yeah, that's what the question looks for. So while we're going to calculate the correct initial slope to hit a 0 here, we have to actually take the third shot to get the right values. So let's use our formula. Now I'll try and use it off the top of my head here. v0 is equal to the bottom one plus a proportion of the, let me see now, it's the right formula. Well, the thing is, right, I actually think this is, I just, it's a bit difficult for me to check right now, but sure, I'm going to be plugging in this value into Excel and I can see if it hits it or not, if you know what I mean. So I'm gonna basically change this on Excel to the right thing, and I should end up with what I'm supposed to get down here, which is my 0. Okay. So let's see, what are we talking about here? VA was our first slope, which was 0. Y of x1 is what we're supposed to do, is 0. Minus YA is our first shot, which turned out to be minus 17.385. That's minus 17.385. YB then is our second shot, 42.615 minus first shot minus 17.385, and then the difference between the two slopes, 10 minus 0. I'm going to get some mathematical software going just for a good calculator. I'm just going to pause the video. So I do this to find significant figures. I get, oh, exactly 2.8975. So I actually have to run it again. So like I'll do the first one, m1 is equal to the previous m value, which was 0 plus step size of 2 times previous slope, and the slope of m is v, and the previous v is 2.8975. Whatever that comes out to be, that being equals to find significant figures. 5.795. And the rest I'm going to do in Excel. I suppose I should have just done the first one in Excel. 2.8975. So I end up with, so that's the approximation. So that's m of 2 is approximated by 5.795, and you keep on going, and you'll also get m of 4 is approximately 3.59. So that's how you do that one by hand.